Well, so although I have planned to start basic of fundamental of rotating machine, but instead of directly jumping there, I thought it would be better that if we could solve a few problems like solved numerical examples from electromechanical energy conservation. This is the last lecture on this set topic. So I have taken, like the previous videos, I have taken a few videos from, few snaps from different books. So this, please read this question. The self and mutual inductance of a, for your better understanding, let me just try to zoom it as much as possible. Okay, so whatever, here you can see that I think it's legible. The self and mutual inductance of a doubly excited magnetic system. In the last example, or sorry, last video, we have solved one problem from doubly excited magnetic system with saliency, and here it is a case that is like same thing. We are having a salient pole configuration. Whenever you will understand that if there is saliency, how to understand or how to figure out that there exists some saliency in your rotor is one simple thing. If you notice that here in your LS and LR, they consist some term that is twice of your rotor angle. So if your system is a smooth system having no saliency, then you will find that this will become independent of theta. Like if your rotor, what I am trying to say, just let me draw it quickly here, that if you have something like this, sorry, more or less a round rotor that is symmetrically placed, then you will find that this LS LR term, it will not contain this kind of means entries that are twice of the rotor angle, right? However, the mutual one will always be a function of your rotor angle, and that is not a big deal. However, let us start. So here in the problem they have said that the winding resistance are negligible, so there is no R present in the winding, or in other words, no IR drop is there. So for stationary rotor at an angle position theta r is equal to 60 degree, find the magnitude and direction of torque when the current in the in the arrow direction of figure 2.21. However, let us figure out what is figure 2.21. Okay. So just a minute. So this is figure 2.21. What is they have said in their question? Clearly, it is a salient pole machine, while the stator is connected with. Sometimes it is connected with DC, and okay, here it is connected with DC. Fine. So no need to consider the alternating one. So what we need to figure out, that we have to find out the magnitude and direction of torque when the current in the arrow direction of figure 2.21. So this is the direction of current flow. we are having this magnitude, we have to find out the torques. So here, for first of all, for a particular angular position, what you need to know, you have to figure out the corresponding inductance values like LS, as it was 0.6 plus 0.2 cos 120 degree. So actually twice of 60 degree. Here it is written 0.6 plus 0.20 cos 2 theta. So this is you will get it is like 0.5 Henry. Similarly LR you can calculate and you will be getting 0.75 plus 0.3 cos 120 degree, that is 0.6 Henry, and the mutual one is 0.8 cos 60 degree, that is 0.40 Henry. So we got all this. Now what we need to find out, that is another thing, how these are dependent on the angular position. So this one will be, you can calculate, the value will be 0.3464 DLR d theta. Here the value is minus 0.52. It is very easy, just you have to evaluate the like 0.6 plus cos 2, you just have to take d theta of that. For your means easy to understand, I am doing this. Actually it was 0.8, sorry, let me do it clearly. Right, it was the expression 0.8 cos theta. So dLSR d theta, how we'll get it? 0.8 and then minus sin theta. So for the other two, DLS and DLR, you have to do the same thing, and you will find it will give you minus 0.693, right? So what about the expression of torque? Expression of torque is what we know, that basically how we get the torque expression, that is by doing delta theta of our co-energy. So here it is half I square DLS, sorry, I square DLS d theta plus half IR square DLR d theta plus IS IR DMSR d theta. So if you evaluate, you will get the value that will give you something. This T, you will, if you evaluate, you will get minus 233.88 Newton meter. So obviously, if torque is negative, it indicates it will try to rotate the rotor in opposite direction. Which direction it is indicating? Here, this is the indication. So means even without doing mathematics, we can understand this, because the way we are feeding this to, it is like that. Theta means the torque is negative, means what? The torque is try to minimize this theta angle, so it can align these two, right? And what you will get by aligning these two, see here the way they are producing this field, it will basically try to means orient them. And as I have mentioned in my earlier videos, that it is always the nature of the total torque of the magnetic circuit to minimize the air gap, because if you increase the air gap, you are actually increasing the size of the magnetic reservoir present in your system, and that can store more energy, which is contrary with that the principle of energy conservation. So that is why it is decided that we need. So here now one thing it is clear that the torque is negative. Now so it is clear that even we can figure out, even if we do not understand, and even if we do not find out the means expression of torque, we can intuitively sense that it must be negative the way we have calculated it. Otherwise there is no way out. Torque must be of, and this is a very basic thing, that for any stable structure your torque must be in opposition to your direction of motion. Otherwise how it can happen? Like if it, when both of them are trying to support each other, then there will be a problem. Obviously don't get confused that in case of motor the torque and the speed they are in the same direction. So apparently my present statement is, you may find it contradictory, but what I am trying to tell you or make you understand, you will gradually get more of it. So when the torque is negative, now this is the value of torque. So another part of the question, what is there? Okay, they have changed the current direction. Now while the stator current direction, rotor current direction has changed, only thing what you will have, the torque will become positive. Why positive? Because you can see for the second part you will have something like let me write down the expression, then you will get more of it. Even expressions sometimes speak a lot about the means mathematical expression speaks a lot about their physics and construction. So here you can see that basically the previous case, when we got the, just let me check, when we got the positive value, negative value, the main contribution was from this part, right? This was contributing. Try to understand one thing, that this is a very important thing, and that is why I have picked up this example, so I can tell more about this. Like in any electromechanical system, most of the time you will find that torque that is produced by mutual interaction. The third term, this one is produced by the mutual interaction of stator and rotor. That will always dominate, and it is quite natural, because if you reduce the saliency and make your rotor a cylindrical one, then what you will get? You will get something like that. This will result in something, it is totally how to tell you, that it will become that, as I told you in the first place, that all this dependence of stator self-inductance and rotor self-inductance on rotor angular position will means rotor and stator self-inductance will not be dependent on the rotor position, when you consider a cylindrical rotor, right? For a cylindrical rotor, so you can easily understand that what would happen to these two terms. These two terms will become zero for the cylindrical rotor machine. But this one, the last one, that is the key, means the main player of producing torque, and that is why it is the governing factor. So what happening in the next case, so when you are changing the direction of current, see, it is giving you a boost. Previously whatever is here, all the two entries, see, you giving you the same contribution, these two part, but this one is giving you a boost. And moreover, why? If you ask yourself that why the means the reluctance torque is not dependent on the rotor current direction. These torque, these two terms, they are due to the saliency of the rotor. If you make them the rotor round shaped, then their dependence on these two terms will be dropped because they will give you zero. If your LS and LR become independent of theta, then these two terms will produce zero. And whenever they are not zero, even in, you see that the expression of current, it is the square. So irrespective of the current flow, they only sense some current is flowing and they will produce some torque, just to make sure the reluctance is minimum of the path. Here you can see that if your this one can align this rotor in this axis, along this axis, then obviously the first two term, that is giving you the negative term, will able to align it, and by aligning it, it can reduce the reluctance of the path, reduce the air gap, reduce the size of the energy reservoir, reduce the total energy stored in the system. So reluctance torque, it is always same irrespective of current direction. So please keep it in your mind that reluctance torque is independent of rotor and stator current direction. However, it is not the case for the mutual torque because it is dependent on the current direction, and that is why it is easy to understand that when you change this current, obviously here previously it was opposite polarity, like here if it was N, rotor was producing S, and if it was S for stator, rotor was producing N here. But now when you change them, change the rotor current, obviously what would happen to the rotor? Rotor polarity will change, and therefore previously if it was trying to align it in this way, now it will try to make it like previously if it was trying to minimize theta, now it will try to minimize 180 minus theta, right? Just try to rotate it one turn and then it will align it. And if you consider the first two player, once you cross the 90 degree, then they are quite okay. Actually they cannot say much, their demand is very simple. They are only praying that please make sure the reluctance is minimum. That is the nature of the reluctance torque, but not the nature of this third term, that is due to mutual. This one always try to align them as per the mutual current direction, and you will get here okay, what is the last part? The last part is okay. Obviously, it is very simple. The last part actually you are finding the reluctance torque, like third part. So what is the second part, that is like just a minute. So in the next part, they are actually asking that the rotor winding is now short circuited, that means the rotor current is zero, and the stator current, sinusoidal current is flowing of 20 ampere flows in the stator winding. Basically, it is a case of means a very popular machine in our uh, means electrical machine, that is known as salient pole synchronous machine, and if you short its stator, it behaves like a reluctance motor. So let us study this, what is here. So for the second part, what you will get, that the rotor circuit will be what, basically the rotor circuit voltage is 0. Now generally VR is equal to what, IR plus d psi r dt. So you can understand that if VR is equal to 0, then it implies we have already considered I0 and R0. So this implies d psi r dt is equal to 0, right? Now what is psi r? Psi r is equal to LR plus, sorry, IR, we cannot say IR is 0, plus MR in RS IS, right? So what we can see, that this party d psi r dt 0 implies d dt of LRIR plus MRS IS. Let me check whether it's recording or not. Yeah. So LRIR plus MRS IS, that will be 0. So that results in d dt of LRIR is equal to minus d dt of MRS IS, right? Or in other words, you can say that IR is equal to fine. Now if that is the case, what is IS? IS is equal to root 220 sine omega t. So in this formula you will get, if you put the values of MSR and LR, you will get it we are getting these values from here. So this will give us so we get the expression of IR. Now we have to figure out the value for our torque with this voltage. So for torque with this voltage, what we will be getting, sorry, this one is minus 0.693. So here, what is IS? IS was 20 root 2 sine omega t. So half 20 root 2 sine omega t, its whole square, minus 0.3464 plus half. We can get the expression of IR from the previous page. Here it is IR. So you should write IR is equal to minus 40 root 2 by 3 sine omega t whole square minus 0.52. Then another term is 20 root 2 minus 40 root 2 by 3 into minus 0.693 into sine square omega t. So if you solve this complicated expression, what you will get, it's like minus 138.56 minus 92.45 plus 369.60 sine square omega t, and this further can be broken as 138.59 and this part is 1 minus cos 2 omega t by 2. So average torque is how much? That is and what would be the direction of average torque? It is that in clockwise direction. Fine. Now we have to figure out that the third part is repeat if the voltage applied on the stator winding is sinusoidal and its magnitude is 314 VRMS at 50 Hz for the values. Okay, so see here. Now when the voltage impressed at a stator winding is given, like I am considering the third part. Again Rs is 0, so it is d psi s dt. Now if it is d psi s dt, then okay, so d psi s dt. So now what is psi s? Psi s is like previously, it is LSIS plus MSIR IR. Now IS is equal to LSIS minus MSR. Here I am assuming MSR is equal to MRS. So MSR LR IS. So basically this gives us LS minus MSR square by LR IS, we can for sake of representation we can boil this total thing as ls dash. So what is ls dash? You can figure out the value of ls dash also. Ls dash is ls minus msr square by lr. So it is, what was your ls? Ls was 0.5 minus 0.4 square divided by 0.6. We are getting this value from the very first calculation. Here, and for all that case we are considering the initial position is 60 degree, that is why we are getting these values. Right, so what we will be getting, it is 0.23 Henry. Right, now your Vs is equal to what? So it is what we are getting here, it is 314 root 2 sine omega t. Right, now if that is the case, then we can figure out is ls dash by integrating this or you can write it like it's an indefinite integral. So what you will be getting here is minus 314 root 2 by your 314. Here we are assuming omega is equal to 314. So 314 root 2 by cos omega t. Right, so you will be getting something like minus root 2 cos 314t. So if that is the case, then obviously you can figure out this is ls dash is, and you know ls dash is 0.23. So from this expression is minus 2 cos 314t. So from this expression you can find out the value of is, that will be minus 6.15 cos 314t. Right, now what about ir is also related to is. You can figure out that will be minus msr by lr is. So that will give you some 4.1 cos 314t. Right, now for that, what expression of torque you will get? Again we are starting with that theta is equal to 30 degree, 60 degree, otherwise everything will be changed. Cos 314 t whole square plus half 4.1 cos 314 t whole square. Here we have to write ls. What is ls? Means dls d theta. This term remains constant. This is dls d theta. Here we need to write dlr d theta. That is, what is the value of dlr d theta? 0.52. This is dlr d theta. Then we have to write the last term, that is is into ir into your dmsr theta. So So what is dA measure theta? That was minus 0.693 from our previous calculation. So if you means you will get something like 6.561 plus cos 628t by 2, and the average value of which will be fine. Now what is the last part? Last part is also very simple. You can do it by your own. However, if you insist me to do the same, then I can do it. But the last part, actually what is there in the last part and what is the essence of that last part? Here you can see it is basically relevant for synchronous generator, right? Previously all the three part A, B, C were for motors. Now we are going to synchronous generator having salient rotor structure. So let me do it. Although it is quite straightforward, but still let me solve it. So what you will get here for the last part, this one D, there will be where you can write Vs is equal to, since Rs is 0, so first term is 0 plus ddt 12 plus sorry, let me write it clearly, ddt psi s, and similarly Vr is equal to ddt psi r. And what is psi s? Psi s is lsis plus msr ir, and psi r is lr ir plus mrs is, and we are assuming mrs is equal to msr. So here if we do this, then we can figure out the expression of psi s and psi r. Psi s will be how much? Psi s will be 0.6 plus cos 0.20 cos 2 theta r, that is for your ls, and to is is how much? Is, we know that is is written that rotor speed is given for the value of current given in part AI. So obviously AI, your it is means A1 is 20 ampere DC, so here it is 20 ampere, right? I suggest you can solve, or you can for your better reference, what you can do, that when I solve a problem in this video, you just take the snap or screenshot of the first page. So whenever you need any value in future, you can directly refer to that screenshot instead of scrolling back to the this original page. So here it is, we are getting it value psi s is equal to 12 plus 4, okay, and another term will be there plus msr, that is 0.8 cos theta r into 10. So solving which you will get 12 plus 4 cos 2 theta r plus 8 cos theta r. And similarly in your psi r you will be getting 7.5 plus 3 cos 2 theta r plus 16 cos theta r, right? So this is psi s and this is psi r. Now we have to write the stator voltage equation, and that is very simple thing to write. Like it will be stator voltage is Vs with speed, like instead of doing it with respect to time, what we can do it with respect to like dummy variable, or not dummy variable. What we can consider that we know d theta r dt is 20 rad per second, so that is given. So this d theta r, like we can replace this dt by d theta r by 20. So here it was d dt psi s. Now you can write it like 20 times d theta r, whatever you are having here, 12 plus 4 cos 2 theta r plus 8 cos theta r. So that will give you the voltage equation. Vs is equal to, you will have minus 160 sin theta r plus sin 2 theta r, right? And similarly you can find out Vr. So if you solve for Vr, you will get it is minus 48 sin theta r plus 3 sin 2 theta r, right? So let us go to the next example. So now let us consider problem number 2. Here the air gap under the poles of a DC machine is not uniform. The bearings are not uniform. It is slightly is tilted to one end of your pole shoe. We have to find an expression for this unbalanced magnetic pull on the armature. So I have selected this example because this example will give you an insight that why a symmetrical placement of the armature inside our winding, or means better to say symmetrical placement of the rotor, is very important with respect to balanced torque generation and others. So here a two-pole DC machine has armature displaced by an amount of 0.1 millimeter. Other data are as follows: air gap flux density 0.8 Tesla, area under each pole 200 centimeter square, uniform air gap length 0.6 centimeter, like G is 0.6 and X is 0.1. So how can we proceed? Like first of all, what is the the force with which a pole pulls that one, means each pole pulls the armature is how much? It is where this Bg is the AP is the pole area, right? Now, if that is the case, then at the side of air gap of length G plus X, what would be the value of, means value of like, means how much it will be affected due to that shift. Just a minute. So AP is the pole area. Now what you can write here, that the force of this one which is shifted by an amount G plus X, how much it would be, like the extra, means reduction of force as well as amplification of force or one pole that is somewhat away from this and the one which is having, sorry. So you can get it clearly that the force with armature with the force means exerted by the pole that is at a distance G plus X, or having an air gap length G plus X, will be how much? Half, and similarly for the other one it will be how much? Or we can write it like, since this one is larger force in comparison with this one, we can write it plus minus to find out the difference. So here you can see one thing that is very clear, that when your x is 0, then both the sides are 1 and these two forces cancel out each other. But when it is not, then you will have something like bg square by mu naught ap gx by g square minus x square. So if you put all the values, you will find it is 169.76 Newton. And now you can understand that with this one, 167.96 Newton, your torque and how it can alter the total machine characteristics. And obviously, if you have this kind of unbalanced pull towards one pole, then that will obviously alter your machine performance. So what happened in some cases when we fail to ensure proper air gap or symmetrical air gap between the pole shoes and armature, then machine means your efficiency of the machine is getting affected by a huge amount. So that is what is we should keep in our mind, that when we will design a machine, we should make sure that air gap must be uniform. Otherwise, not only it is a matter of efficiency, but due to this unbalanced force, your machine mechanical part will experience more wear and tear action, and within a very short time period, your machine bearing, you have to replace your bearing by a new one. So all these are the disadvantages of placing your armature in a manner that is not symmetrical, right? Now let us go to the next problem. Now let us consider the next problem. What it states that this adjacent figure shows a slot containing ZS conductors. Of each conductor carries a current of I amperes. So total current is ZSI. The iron part of the magnetic circuit is assumed to have infinite permeability. That means there is no energy stored in the iron part. Find the variation of the flux density in the part of the slot above the conductor portion and 2 occupied by the conductors. Then find an expression of leakage flux above the conductor portion. Then find the electromagnetic force created by the slot leakage flux present above the armature conductor portion. So this problem is very important in different aspects. Like if you consider here, there are several things. Like we have to understand that how means a leakage is not only detrimental in terms of loss or other things what we have already studied in our transformer, but in case of a rotating machine or means a system that is having any movable structure, leakage can also produce some torque, and that any thing that is undesirable, that is whatever consequences that undesirable phenomena will produce, that all those consequences are also undesirable. We'll see that. Now let us see. Okay, let me just take it to another page. So let us start. First of all, see that reluctance of the iron path is negligible. So all the MMF you consider, like MMF is comparable to EMF, so you can expect that MMFs are like, if you consider these total as a series connected magnetic circuit, you can expect most of the MMF present here. Like if you place a voltage say 100 ohm and 1 ohm in series together and apply some voltage, you can expect that the lion's share of the voltage drop will take place across your 100 ohm resistance, not 1 ohm. So by similar argument, you can see that the main MMF will present there in the your air gap, and what would be the value of that MMF? That is just a minute. So it is I into ZS, where IZS is the total number of MMF, and this one is what you know that this is H is what magnetic field intensity, whose unit is ampere turn per meter. So here it is this meter is given by this WS, that is the this slot width, and this slot width if you multiply, then you will get this IZS. Here I am intentionally explaining all these kind of like all these in detail so that you can get it properly, right? Now Let me draw the diagram here. It's not given. Let me draw it. Otherwise, we will have a problem. Like, let me take help of this. I do not know how much I can do. Let us import this once again. So this is our structure. Now let me draw the value of our BH curve, like what will be the nature of that. So you can understand that it's like here, if we assume something, a path while this is having y, this one is y. Okay, let me draw it once again clearly. Obviously, magnetic flux lines should not cut each other, and means if it appears to you that they are means colliding with each other, that is my fault of drawing, but it is not the actual case. Now, this one is like, you can consider this aperture is x. So what we are trying to draw here is that, like, if we take something so actually I'm trying to draw this, you can say that how flux density varies over the slot depth. That is my concern here. Now you can understand that flux density is varying over the slot depth. It's like here it is, see, if you consider this one, the maximum value of y, as long as you are considering the conductor, here you will have a flux change, it will be linearly varying, right? The whole thing here in this way, I am plotting B and say it is the direction of I am moving, and in this axis I am plotting something that when I am trying to move out in this direction, this distance is plotted here, like if this is denoted by h or something, so here it is h, and how long it will be vary in a linear manner as long as we are having h here. Why? Why? Still why? Because if you means gradually say when your h is 0, that means you are particularly not enclosing any current carrying conductor. Now as you move on, means in this upward direction, then what you are actually doing, let me show you. You are enclosing this portion of your current carrying coil, and more you move upward, more amount of current will be enclosed by you, right? You are actually basically applying that. You can apply that ampere circuital law also, that H dot dl is equal to the line integral of H dot dl is equal to surface integral of J dot ds. So obviously if you increase the surface area here, that will obviously cause a change. And if you are not, or if you are quite apprehensive of considering all these what I can say elite mathematical consideration, you can just apply your common sense and slightly intuitively you can understand that if we enclose a small amount of current here, then obviously the amount of H will also be small, and as we move up, as we start covering up more cross-sectional area of the conductor, then obviously we will be able to enclose more amount of current, and that will enclose or increase the. So how it will vary? Obviously if we know that formula of resistance, R is equal to rho L, by A, you can find out the conductance, or you can always understand that R is I is inversely proportional with R, so I is directly proportional with A. So for a constant current density J, if you increase the area, obviously current will vary linearly, and it will vary till you reach the terminal point, that is Y. What is Y? Y is this one. After that, even if you move upward, you are not able to get any more current. So the H will remain constant. And if H remains constant, then what you will have? B is mu H, so it will be a straight line. So even if you move in this direction, your B, it is I have drawn a wrong curve. It is like this, right? So till Y it is increasing, and so you may ask me the question that why it is linearly varying. Obviously this conductor is not that kind of ferromagnetic material, or means it is not a magnetic material that we can consider or drop the consideration here also. While we are considering this red color area, this shaded area, there also we can apply this so mu naught is remain constant whether you are considering this area or this area or this area, right? This material's mu r is very small, so it is almost the resultant permeability almost like here. So this is the case. Now when you are only change is there when you are increasing the amount of area or the amount of current enclosed by your magnetic path, you are getting more H and therefore more B. But once you reach here, this say By is equal to mu Hy. After that Hy remains constant, because if you move upward, then you cannot get any more current carrying material. So this is the nature of the curve. So I hope it's clear. Now if you what is Hy? Now you tell me what is Hy for the total, when you consider the total enclosed of that one, then you will get it is mu 0 Izs by Ws. Why? Because here you can see that I have written HS, it should be WS. So here you can see that why it is we are having this expression. Now what we can write more, that it is mu naught IZS by WS, and this one we can say this is y. So we can say here in this, what is the slope of this line, if this value is y, then the slope of this line is y by h. So it is till this point it is h1. So at this here it is h1. So my main intention, although this chapter is not that much important, but why I am picking up all these numerical examples. So before we start the rotating machine, you already have a firm understanding how things can be complicated when we will start discussing rotating machine. It is not the case of transformer, but it is very simple. It's just magnetizing, demagnetizing, not that. We will have another type of means quantity, another type of signals will be present, that is mechanical signal, and we have to consider them. In case of transformer, everything is in terms of flux and current and voltage, that's it. But now when you move towards the rotating machine, the beauty of the rotating machine is that it is not only limited to flux and current and voltage. There you will get also force, torque, and those force and torque, they always whenever there is some flux means flux change, there will be some force, there will be some torque. Obviously in transformer also, if you recall a long back, I asked you one question, that why do you think that transformer winding do not experience any force? So many of you didn't answer. Obviously transformer secondary winding and primary winding, they experience means higher amount of force when you load the transformer, but as transformer is not moving, so those forces or torques on the coil of the transformer cannot create that kind of complexity or means adverse condition. But here in rotating machine they can. Now see, this slot depth reduction is 0 at base. So what we can write here is that from this expression, that this is the expression of Hy. So with this we can write that By is equal to mu naught, this whole thing, yes, this IZS Y by H1 WS. Now here one thing is very clear, that the flux density variation over this slot depth H1 plus H2, it's like So let us consider the amount of uh, there is one part like part A. Find the variation of flux density over the part of the slot above the conductor. Okay. So we have already solved and drawn this one. Now let us consider the amount of slot leakage flux. Please pay your attention. The amount of slot leakage flux is what? That is why it is H2, because slot leakage will start when you will consider there is nothing and pure you are considering the air gap. So slot leakage you will be getting so obvious question that may come in your mind, that why it is that means only H2, not the entire H, that is H1 plus H2. Why only H2 you are considering? The answer is very simple, that whenever you are having that current carrying conductor, it is not leakage flux, it is linked with your current carrying conductor. But when you move beyond that, then only the expression of leakage comes in the picture. Prior to that, if you move upward, then you are also enclosing more number of current, or more amount of current. So that is a issue. Now see that this is the slot leakage flux, and what is L? L is the like here this H2 and L, they are actually giving us the area. This L is the you can say this is a technical term. Let me tell you in a very simple manner. What is L? Suppose if we take a side view of this slot, side view of this slot means like say I am drawing this is the front view. If I draw the side view of the slot, you will get something like this. A slot is like a this kind of means structure, solid structure. Now here this length is L. What is H? Now what is your conductor? Conductor is here. So basically you can consider that it is a structure the base of which to a certain height is filled up with your conductor, right? And so here it is a parallel pipe that, and this conductor it's dividing it in two sections. One is hollow parallel pipe with this H2, and here in this direction it is L, and this side it is H1, right? So I can draw it with another color so you can understand it clearly that so this is the conductor, and this upper portion what is the area of this one? This is H2L. If you sorry, not this side, this is WSL. Yeah, what is WS? This is our WS. And what is this side area? The side area above the conductor region is this one. Good. This is the side area. So what is that? Why this side area we are considering? We are considering this side area because this side area is experiencing the flux density. What is that flux density? Flux density perpendicular to this area is like flux is perpendicular to this, and flux, this dotted one line is here, right? The flux is perpendicular to this area, and this area is how much? It is H2 into L. It is the rectangle with this side L, this side H2. So the total area is this H2L. Right, now one more important observation what we can make here, that this slot leakage flux, it is proportional to slot depth. This H2 is what? H2 is your slot depth, and sorry, and this flux is inversely proportional to the slot width. So what we can, in a nutshell, what conclusion we can draw, that if I want to so obvious consideration after reading this line will be like, what is harm if we go on means increasing the slot width? Why we can't do that? What are the things that will means constrain our means slot width expansion? There are several factors like how many number of conductors you need, how many like if you increase the slot width, obviously you are means the total peripheral length of that armature is pi d, and for a given d, your pi d is the amount is constant, so you cannot go beyond that. Now say pi d is equal to 100 centimeter. Now if you take a slot width of 1 centimeter and between two adjacent slot there is another gap of 1 centimeter, how many slots we can accommodate? That is 50 number of slots. However, if you change it to say 2 centimeter and 2 centimeter, then the number of slots will reduce to 25. So obviously it is a matter of choice that only we should try our best to reduce the leakage reactance, but only reduction of leakage reactance is not always possible below certain limit, right? So now problem number C, part C of that problem, find the electromagnetic force Fe created by the slot leakage flux present above the conductor portion. Obviously inside conductor portion it will be quite complicated due to means different value of current enclosed by the path, but once we cross the total conductor or cover the total conductor area, then the force can easily be calculated. So what we can do here is that instead of directly finding out force, we can start with finding out the expression of your that energy, which is half v square by mu naught or you can write it like Bs to clearly indicate it is the slot flux density. So what you will get it here, it's very simple thing, like you will get it this value, and for this one if you replace this B by your mu h, B is equal to mu h square, then what you will get here, you will have mu 0 square h square here, or h square xl ws by mu naught, then it will give you half mu naught, then h square can further be simplified as I square z square xl ws by here it will be ws square, so basically it will give you this. This is the complete expression of force created, sorry, the energy Now, how to get the force? In order to get the force, what you need to do is you have to take that. Now, obviously, what is this x? That is also, we must understand that what is this x? If we go back to our picture, then whether it is this h2 is x, like this x is something, it is here. As we move in upward direction, our conductor radius, then that is x, or x is something like x is 0 when you are on the conductor's surface, upper surface of the conductor, and x is h2 when you reach the here. Like when you are here, then x is 0, and when you are here, x is h2. And so our question is that, do you think that which x we are considering? Obviously, x here is the depth of the slot above your conductor portion. So if you do it, you will get it like half mu naught I square z square L by Ws. So it is very clear, if you want to minimize this force, again you have to, like in the previous discussion we have seen that if I want to reduce the leakage flux, I need to reduce the slot depth and increase the slot width. So same thing here. Here not only the slot depth, reduction of slot depth won't help much. Here you have to reduce this L, like the slot length must be reduced, and the slot width must be increased to a certain value. However, we must consider that what are the pros and cons of going for such a dimension. Now let us come to the last part of the discussion, that is the direction of force. What is the question? For I is equal to some value is given, find the direction and magnitude of the magnetic force found in part C, means the previous part. There are two conductors in slot, embedded length is 1 meter and slot width is 5 centimeters. So all the values are given. Basically we need to find out the force. So just it's very simple, half into 4 pi into 10 to the power minus 7 into I value is given there. I is root 2000 sine 341 t. Square. Then what is ZS? ZS is like two conductors, so ZS is 2, and then L is 1, and this one is 5 into 10 to the power minus 2. So basically this as per the calculation given will give you something like this, 32 pi 1 minus cos 2 omega t by 2. And if you try to take their average value of which will be something like 50.265 Newton. Not a matter of joke. 50.265 Newton, it's a huge amount. Now let us consider another problem. So please read the problem. For a two-pole DC machine, a conductor on the armature carries a current of I ampere. Derive an expression for the electromagnetic force Fe on the conductor. Use the result obtained in part A to determine the force between parallel conductors carrying current I1 and I2 in the same direction. So first of all, this is the structure you can see here, and also the solution part of the solution. I got it here in the snap, so you can also read it. The basic thing what they want to mention, that when the conductor current is zero, the means if there is no flow of conductor current, then obviously armature reaction is zero, and the air gap flux distribution due to your north pole and south pole will be uniform over the means polar region. Now this uh, uniform flux density, they have assumed it as B1, and it's getting B1 is equal to mu 0 I by 2G, right? While they are considering that conductor carries current I, obviously it is I, so it is I by 2G. Why 2G? Because you have to consider both the path, right? Now here obviously we are assuming that whatever reluctance is there is present only in the air gap. The means magnetic part or the magnetic material part of the machine is having infinite high permeability. Now if that is the case, so let us draw a few diagrams, like when there is no current, means zero armature reaction, what you will have here. So fluxes will be directly in this form. Now when you allow flow of current, here there are two groups, and or the slots are there in which you have placed current carrying conductors. Now when you place the current carrying conductor, obviously what will happen? They will produce their own set of mmf by this, sorry, say this one is cross, or even if you consider this one is dot, you can also figure it out. Like dot means the current is emitting out of this plane of this board, so basically you are getting something in counterclockwise direction. So obviously along the armature field is totally perpendicular and cross magnetizing in nature. So what happened to your resultant field, what we have studied, that it will cause a shift, and that is quite easy to understand, like what we will have here. Let me draw it. So due to this, here you will get a heavy amount of, because this side you can see that these blue lines and this white flux produced by the field, they are acting in same direction, and in the other side they are acting in opposition. So what you can expect means crowding of these flux lines here in this region, or strengthening of the field, and in the other side it is. So here you can see that this side it is. Oh, I have made a mistake. They have shown it is cross. So just let us change it. If it is cross, what would happen to this direction? Just it will cause a reversal in the direction of the field, sorry, direction of the armature mmf, right? Armature mmf direction will be reverse, and therefore what you will have here, you will have something. Here it is theta minus theta 1 and rounding of like flux lines in this side. Okay, so now here one thing is clear, that both side the air gap is uniform. Like we have also studied the problem where air gap is not symmetrical with respect to machine axis, but here the air gap is uniform. So that is one good thing. Now here what we can write, like this side, this flux we can write, it is our, say, just a minute, where is this? So this side it will be b minus b1, and this side is b plus b1, right? Due to this crowding of flux, like we are considering this b1 is what? b1 is mu 0 I by 2g So now this one is b plus b1. So what you will get here, like the W field is equal to how much? That is something half. We can have two sides. One is b plus b1 square by mu naught minus half b minus b1 square by mu naught glx. So if you do not have this kind of means disturbance due to that. Now one thing is means what does it indicate when B1 is 0, this W field is 0. So try to relate it with your physical system. When there is no current flowing through your armature, can you expect that DC motor armature will rotate? No, because the energy is 0. But whenever you allow flow of current through your armature, you can see that from this expression also we can explain why there is, whenever there is a flow of current, then only you can get some B1 from your armature. Until unless you allow flow of current through your motor armature, their B1 will be 0, and therefore the two sides will cancel out each other, like you have W field is equal to 0. Now, obvious question that becomes in your mind, that why so? Like, even if we are having this, means we can have energy stored in a single excited system also. So, what does this indicate? Like, does it indicate that there will be nothing in the air gap region? Even if we do not, it may so happen that we do not excite, but that why does it imply that there will be zero energy in the air gap? So think about it. So if you means simplify this, okay, let me quickly explain the question that I am trying to ask you. That if we make B1 0, then also the system will behave like a single excited system, and in that case also you should have some energy stored in your magnetic path, means this air gap region, these regions. So why they are not, means we are not getting something finite, rather we are getting 0 here? That was my question, which you should think and means understand, that why whenever it is 0, then also it is a singly excited system, and we can always expect some energy there in the air gap, but here it is not there in the air gap. Why so? Okay, so for that expression of energy, if you do simple algebraic manipulation, what you will get, so this one is b, means a plus b whole square minus a minus b whole square, so that should result in our 4ab, that is 4b b1, so it results 2b b1 glx, then mu naught. Okay, fine, no issue. Now that substitution of B1, what is B1? B1 is your mu naught I by 2G. So you replace it here. So what you will get, W field is equal to 2B glx by mu naught mu 0 I by 2G. So these two cancel out each other. So this will give us BLXI. So what is B, L, X and I? What is that? The axial length of the conductor is L, and what is your X? Think about it. What is X? Is does here the X represent the slot depth? But there is no such kind of slot or such consideration is here. So what is X actually here in this picture? We are doing something, we are getting some result, it's fine. But what is this small x? X is the small amount of displacement of this conductor in any direction. Like we are having this field, and when you have this, this one is your x, right? This small shift is x. So here you are getting this, and obviously the expression of force should be free from that x, because the idea is when your machine is at under polar region, then it is energy x is 0, and when it is interpolar region, it is the energy is maximum. And you should not be means find it too surprising, because if you consider that case of Barlow's wheel or something, when it is under pole phase, then there is perfect cancellation, but when it moves to that interpolar region, it means realize that kind of means interaction, and that gives us a huge amount of torque, and that by virtue of its inertial tendency, it moves a certain part. So all these are there. Now think about that what you will have a field electronics gadgets. So whatever it's dw, sorry, this one is dw del x. So you will get what? This is our very popular expression that force is constant. It is dependent on the current. It is not that one. It is the energy. What energy is minimum when it is under polar region, and energy is maximum when it is in interpolar region. But the force remain constant, right? Now, if that is the case, then what the part is there? Derive an expression of, okay. In B, they are asking use the result obtained, determine the force between two parallel conductors carrying current I1 and I2. Uh, this this is a kind of disjoint problem, so, and of little interest from electrical machine perspective, so I would like to skip that one and go to our next problem. So here a problem is given that two coupled coils, self and mutual inductance are given. Now over a certain range of linear displacement x, first coil is excited by a constant current of 20 ampere. The second one is by minus 10 ampere. Now mechanical work, we have to find out something. So it's very easy. You can do it without much giving much thought of it. It's very straightforward, like this W field, as it is a multiply excited one. So but here we would like to utilize the expression of co-energy, because please note that here it's means the flux linkage is not mentioned. So we will exploit the concept of co-energy here. And what is co-energy? Co-energy is sorry, we are assuming L12 is equal to L21 or MSR is equal to MRS. So L21 or 12 is equal to I1 I2. Basically it was half plus half L21 I1 I2, but as we are assuming I1 L21 is equal to L12, so we can sorry drop this part and we can get this one, this. So if you put the values like it times this one is, what is your x change from 0.5 to 1. Now initially we do not know what is x, but keeping x in, we can put the expression of current here and we will get the expression like it is half 2 plus 1 by 2x into 20 square plus half your 1 plus 1 by 2x into 10 square, sorry, minus 10 square or 10 square, it is quite okay. And here it is 20 minus 10, it is 1 by 2x. So if this is the case, then we can write it, if we simplify, we will get it something like 450 plus 25 by x. So what is your force? Force is it will give you, if you take del x of this, it will give you right. Now mechanical work done if x change from 0.5 to 1 meter. So basically the same thing, how to find out that mechanical work done when your force is varying. So it is so here xf is how much? 1, x naught is 0.5, then this one is minus 25 by x square dx, so you will get it minus 25 joule. So why it is minus 25 joule? Like mechanical work done if x changes from 0.5 to 1. So what is x? First of all, you must understand that x is something that is the displacement between two mutually coupled coils. And when you are trying to reduce x, right, while the two coils are carrying current in opposite direction, right, you can see that first coil 20 ampere, second coil 10 minus 10 ampere. So it is quite clear that due to this, what you will have something uh, like, how to explain, just this we are trying to reduce this, why it is minus 25 joule. So minus 25 joule, because when you are trying to make x, means if you increase x, then basically you do not have to do any work, rather you are getting the stored energy from that system. This is the meaning of this minus 25 joule. Like, you do not have to do any work, you will get, rather you will get some extra energy out of your system when you will try to move these two away from each other, right? And why so? Because if you consider the expression, here you can see that the dimension of x is appearing in the denominator part. So basically, if you increase x, basically you are reducing the inductor present in your system. So whenever you are trying to reduce the amount of inductance present in your system, if you reduce the inductance, then obviously the energy that the previous system can store, that is half Li square. Now if it is L dash, why L dash is less than L, obviously the new energy stored, or the new capacity of the system, will be lesser than the previous or the original one. So therefore, what system will do? System will send you back the additional energy, namely the energy that is you will get by doing this. If you keep current constant, then the system will try to give you back this energy. Now, had we have something like this x appear in the numerator, you will always see that here, if you try to increase x, then you have to spend more energy. But here the scenario is reversed. You are getting back the energy. Now, energy supplied by each electrical source we have to find out. So we have to find out what is the amount of energy stored by each electrical source. So what we can write here, like we can write the electrical energy. So let me check whether it is recording or not. Yeah. WE1 is what? It is say this is lambda 1, this is lambda 2. Right. So what you will get here, I remain constant. For one source I remain constant. So if it is I1, it is I1. So you are having this I1 lambda 1 now. Please note that it is like the result of integration depends on the two terminal values of your operation, rather than the path of which you have chosen to reach from lambda to lambda 1, because here we are considering the lossless system. If it is non-conservative or lossy system, then path will matter. In some path we will find that hysteresis loss and recurrent loss are more. In some other path we may find that hysteresis loss and recurrent loss are less. However, here it is not present. So you can follow any path and you will get this result. So now lambda 1, we know it is like L11 I1 plus L12 I2. So this one is like, if you put the values, you will get something like 40 plus 5 by x, while obviously I2 is minus 10, I1 is 20, and that expression of L11 and L12 you can get it from the problem. So now lambda 1 at x is equal to 1 is how much? 45, and lambda 2 at x is equal to 1 will be how much? 50. So basically it is that delta WE1, if you calculate, it is 20, here it is 45 minus 50, that is minus 100 joule, right? Similarly, you can find out the energy WE2, that is how much? That is similarly applying the concept of lossless energy system, it is lambda 2 at x is equal to 1 minus lambda 2 at x is equal to 0.5. So if you take, it is minus 10, here lambda 2 is how much? Lambda 2 is equal to that L12 I1 plus L22 I2. So L12 I1 you will get it like minus 10 plus 5 by x. So for x is equal to 1, lambda 2 is minus 5 at x is equal to 1, and lambda 2 is equal to 0, probably, yeah, 0 at x is equal to 0.5. So it is like we are getting minus 10 minus 5, so this is 50 joule. So total electrical energy is how much? That is your delta WE is delta WE1 plus delta WE2, that is minus 100 plus 50 is equal to minus 50 joule. So the energy supplied by each electrical source, the total energy supplied by electrical source is minus 50 joule, and that is the exact amount of no, not exact, like that in mechanical part it is minus 25 joule. So what is the amount of energy stored there? Like for, sorry. Now we have to find out the change in the field energy. The change in the field energy. So how can we do that? For changing field energy, you need to obtain that different value of beta. What is beta? Beta is right. So if you put all these values, you will get beta 1 is equal to 2x plus 1 divided by 4x plus 3, right? And then beta 2 is obviously beta 2, how can you get beta 2? That is beta 1 by d. So means L11 by d. So what is L11? I can show you that it is coming. Just a minute. L11 is 2 plus 1 by 2x, and then it divided by your 2 plus 1 by 2x into 1 by 1 plus 2x minus 1 by 2x whole square. So you can understand that what you will be getting. Among these 4 terms, last term will be cancelled out, remaining term will be there. So remaining term are 2 plus that 1 by 2x plus 2 by 2x, that is something like 2 plus 3 by 2x, and here 2 plus 1 by 2x. So basically we will get 4x plus 1 by 4x plus 3, right? So similarly you can calculate beta 1 2. Beta 1 2, if you calculate, you will get it like so. With all this value, you will, if you put the value of x is equal to 0.5, then you will be getting beta 1 1 is equal to 2 by 5, beta 2 2 is equal to 3 by 5, beta 1 2 is equal to minus 1 by 5, and similarly at x is equal to 1 you will have beta 1 1 is equal to 3 by 7, beta 2 2 is equal to 5 by 7, beta 1 2 is equal to minus 1 by 7, right? Now you can calculate the field energy when it is there. So field energy you can calculate like it is WF is what? It is like, we can write it like WS is equal to half beta 11 square lambda 1 square plus half beta 12 square, sorry, beta 12 square, beta 12 lambda 1, lambda 2 plus half beta 2 2 lambda 2 square. This is the expression of WA, and at x is equal to 0.5, x is equal to 0.5, you can calculate, and you find from this formula we already calculated. Sorry, here this one is applicable for both the value of x. So you know the value of previously we have found out different value of lambda 1, lambda, here lambda 1, lambda 2. You are having these values, right? So you know lambda 1, lambda 2, and now you can find it out. W8 will be how much? At x is equal to 0.5, W8 will be half into 2 by 5 into 50 square. So that will give you something like 500 joule, and WF at x is equal to 1 will be how much? That is half into 3 by 7 into 45 square plus into 5 by 7 into minus 5 square plus minus 1 by 7 into 45 into minus 5. So if you do all this mumbo jumbo, you will be reaching a calculation. It will give you something WF, it is 475 joule. So what you can see that the net difference is, what the net difference is, that is minus 25 joule, and that is quite okay because magnetic field energy is minus 25 joule. Your mechanical work done is minus 25 joule, while the electrical one is somewhere minus 50 joule. So electrical work done minus 50 joule, then minus 25 joule is mechanical work done, and minus 25 joule is stored in the magnetic reservoir. Since all are minus, that means all you are getting actually back. Instead of giving, you are getting. So that concludes this one. Like, this is the problem we have solved.